Okay, so let's get started. This is the 5th lecture, and we are talking about, what are we talking about?
Convolution.
Convolution, right? So anybody remind us what convolution is? You have two functions, say. So convolution, you've got two functions, say on negative pi pi, right? Negative pi pi. And then you define the convolution of these two functions at a point as, come on in. You define the convolution of those two functions at a point as what? See if you can do it.
1 over 2 pi
Yeah.
times the integral
The integral of?
f at y times g at x minus y dy.
Yeah. Okay, so that's the convolution, right? Okay, and we said that this is some sort of like averaging, using a function to average another function. So, for example, if you let, so we mentioned this last time. For example, if we let g be 1 over 2h times the characteristic function of negative h, right? In other words, the interval of length 2h and of height 1 over 2h. Okay, of height 1 over 2h. So it has this massive, it has a massive 1. Okay, and you notice that, right? As we said last time, if we're if g is that function, then what are we going to get? We're going to get g of x minus y. Well, this is going to be 1 when this is going to be 1 when x minus y is close to 0, right? When x minus y is within a half of 0. In other words, when y is within within h, sorry. So when x minus y is within h of 0, sorry. In other words, when y is within h of x, right? So this is going to be 1 when y is within h of x. So in the example, f convolved with this guy would be this thing, but this is going to be 1 when x lies within, sorry, when y lies within x minus h, x plus h, right? Assuming that h is small enough that we're in the interval, say. Okay, and then we get this 1 over 2h thing, and we get dy, right? So ignoring the 1 over 2 pi for a second, ignoring the 1 over 2 pi, it's just a constant. What we're doing is we're averaging the function over the interval centered at h. Okay, that's how you want to think about the convolution operator. Okay, that we're doing some sort of averaging of the function. Okay. So in particular, you want to think of convolution as a smoothing, some sort of smoothing operator. Okay, it improves the smoothness of your function. Okay. Okay. Another remark. Lots of operators. Operators in analysis. Many operators in analysis are defined by taking some function and then convolving it against some other function. Okay, the thing that you're convolving against is called a kernel. Okay, called a kernel. The thing that you're using to smooth your operator. Okay, so these guys are called convolution operators. Convolution operators. And they're all over the place. As we saw last time, right? The partial sum operator is in fact the convolution of f against the Dirichlet kernel. Right? Kai, you look like you have a question.
That's exactly what I was going to ask.
Okay. Yes. Right. So, right, and like as we mentioned last time, right? The question that we're asking is, does this converge in some way back to your original function. In other words, we're asking, does the limit of these convolutions somehow give us back our original function? Okay, so convolution, you want to think of it as a kind of, as a smoothing operator. But you also want to think of it as a multiplication of a way of multiplying functions. So here is the theorem that will make that really, really, really explicit. So properties of convolution. Properties of convolution. If you have f, g, and h, which are all 2 pi periodic integrable functions, okay, and some constant, then f convolved with g plus h equals, as you might expect, f convolved with g plus f convolved with h. Okay. In other words, you have a distributive property, right? Just like back in elementary school. Okay. You also have that you can pull the constant through. So Cf convolved with G is equal to C times F convolved with G is equal to F convolved with C times G. That's sort of obvious. I mean, these both are obvious. We don't really need to prove them. As we mentioned last time, convolution is commutative. That you can see via change of variables. It's also an easy calculation to see that F convolved with G convolved with H is equal to F convolved with G convolved with H. That convolution is associative. Okay. So basically, convolution does what you would want a multiplication to do. Just as a side comment, if you look at the L1 functions that are 2 pi periodic, so people write those functions as on the unit circle. It's what's called a Banach algebra. Okay. In other words, it's a complete normed vector space with an algebra structure that works well with the norm. But anyway, that's not important. It's just a side comment. Okay. So those are the pretty straightforward ones. The fifth and sixth ones are the more important ones. So continuity. So in fact, the convolution of these integrable functions is continuous. Okay. When you take two integrable functions, those guys don't have to be continuous, right? They don't necessarily have to be continuous, but when you convolve them, the result is continuous. Okay, and this you can think of as sort of evidence, like a sort of that idea that convolution is a smoothing operator. Okay. And then the sixth one, and this is the important one for us, that if you take the Fourier transform, if you take the Fourier coefficient of the convolution, you look at the Fourier coefficients of the convolution, that actually gives you the product of the Fourier coefficients of the factors. Okay. So yeah, so kind of like convolution in the function world turns into actual multiplication in the Fourier coefficient world. Okay, so it really is multiplication in some sense. Okay. So you can sort of think about this. So like, remember we had this F convolved with the Dirichlet kernel, right? F convolved with the Dirichlet kernel, well, that's the summation operator, right? That's the summation operator, right? And if you think about the function and the Fourier coefficients of the Dirichlet kernel, right? So what this is saying is that that this equals this. Okay, but that I hope that's actually that should actually be pretty clear to you, because remember, what are the coefficients of the Dirichlet kernel? Anybody remember? It's going to be 1 between negative n and n, right? It's going to be 1 between negative n and n. In other words, it's a characteristic function between n and n, right? This is this, right? And what that's saying is that if you take the Fourier coefficients of the partial sum operator, what you get is just the Fourier coefficient of the original thing, but it will be chopped off. It'll be chopped off between negative n and n, between a certain range of frequencies. Okay, so that's what the partial sum operator does, right? It says we're going to look at only the frequencies between negative n and n. So that should be a capital N. Okay. So anyway, that's just an example of why you might believe this to be true. We'll prove it. We'll prove it to be true in a second, of course. Okay. Okay. So that's just a list of properties of convolution. Really important idea in analysis. In harmonic analysis, one of the big things of studying for many years was you convolve with this thing with a kernel that satisfies certain properties, and you get something called a singular integral operator. The kernel has some singularity, it has some blow up, so this is called a singular integral operator. So that was what I spent years studying. Okay. Let's go for the for continuity. So right. So F and G. Like 2 pi periodic, and Riemann integrable. And our claim is that convolution is actually continuous. Okay, so we're going to prove this by using a fact. So recall that we had this fact at the beginning that integrable functions can be approximated by continuous functions. Okay. So we had the statement. We didn't prove it, but in the appendix it says if f is integrable on some interval AB, then there exists a sequence f sub k of continuous functions. So remember, an integrable means that f is bounded by, also includes that f is bounded by some bound. Okay. So then there exists a sequence of continuous functions such that, well, one, they're all bounded by the same bound. Okay, so they're all nicely bounded. Two, the limit of, oops. limit of the absolute value, the integral of the absolute value of the difference goes to 0 as k goes to infinity. Okay, so in the LP language, this is the LP norm. This is the L1 norm of the difference, right? So it's saying that the L1 distance between in the L1 metric, this sequence converges to that. Okay. In other words, what it's saying is that in the space of Riemann integrable functions, continuous functions are dense in the L1 metric with respect to the L1 metric. Right. So just to rephrase it more in a more cool sounding way, right? Continuous functions are dense with respect to the L1 metric in the integral functions in the space of integrable functions. Okay, so that's what we're going to use. Okay, so our strategy is going to be, let's do it with the, let's show this is true for continuous functions, and then let's show it's true for for integrable functions. Okay, using the fact that we've already got it for the continuous functions. Okay. Okay. So here's the proof. You say, well, let's say that so case 1, assume f and g continuous, right? And we want to show that f convolve with g. Want to show that f convolve with g is continuous. Okay. We're actually going to do something a bit more than that. We'll show that it's uniformly continuous. We don't need to do that, but we'll do it anyway. It's easy enough. It's easy enough, and of course it's true because we're on an interval, so we're on a compact set. So continuous implies uniformly continuous. Continuous is equivalent to uniformly continuous. There. Okay. So okay. So we want to show that this is uniformly continuous. In other words, given any epsilon, there exists delta, such that if you have your 2 points that are within delta of each other, then f convolve with g at one point is within epsilon of f convolve with g at the other point. Right. That's what we want to show. Okay. Okay. So just do it. You just say, well, look, well, what's the convolution, right? Well, so the left-hand side here. So, well, the left-hand side is 1 over 2 pi f of y g times g of x1 minus y dy, right? And then we get minus. I'll just combine them together, minus the convolution of the other guy, which will give us this thing here, x2 minus y dy, between negative pi and pi. Right? Okay. Absolute values. Okay. And the usual move, we use the triangle inequality, right? So we're trying to get the control of the size of this guy, we use the triangle inequality. We go, right, this is going to be absolute value of f times the absolute value of g of x1 minus y minus g of x2 minus y dy, right? Right. So how are we going to make this smaller than, we want this to be smaller than epsilon, so we just say, well, look, this thing is bounded, right? They're both integrable functions, so we say that f is smaller than some b. So this thing is bounded by b, and then g is continuous on the interval, so it's absolutely uniformly continuous, right? So we know that we can choose, since G is uniformly continuous, there exists a delta such that, if G of Z1 minus G of Z2, I'm sorry, if Z1 minus Z2 is smaller than delta, then G of Z1 minus G of Z2 is smaller than epsilon over V times 2 pi. Right? So use that epsilon, right? I'm sorry, use that delta. Use that delta. Then we know that this, x1 and x2 are within delta of each other, so x1 minus y and x2 minus y are within delta of each other, right? And so we get that this thing is going to be bounded by 2 pi epsilon over v, right? And so we get smaller than epsilon. Okay, yes? Are we all right? Any questions? Right, we're trying to show this thing is uniformly continuous. In other words, as long as these points are close to each other, the outputs are going to be close to each other. Right? So we just write down what that means. It means that this difference is going to be small, right? Why is this difference small? Because this is small, and we have, by the continuity of G, this thing is small. Done. That's it.
Wait,
Yeah.
shouldn't bound be epsilon over b because we want it to be less than or equal to epsilon? Because we have an interval form.
So there's a 2 pi here.
Oh, okay.
From here.
Got it.
Okay. Okay. So we have that the convolution is continuous if the functions are continuous, right? And so now we're going to use this lemma to go to integrable functions. Okay. So we say okay. Okay, so case 2, f and g are integrable. Okay, f and g are integrable. Okay, so claim. So first off, start off with these guys, right? So by the lemma, should call this a lemma. So maybe like L1 density, just I'm going to say density lemma. L1 density lemma. Okay, so by the lemma, we have sequences f and g of continuous functions, such that f, such that blah 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 blah, right? That f and gk go to f and g in L1. I'm not gonna rewrite it. So, right, and each of these guys has bounds corresponding to f and g's bounds. So let's say b1 and b2 are the bounds. Okay, so so claim. It suffices to show that the convolution the convolution of these guys converges uniformly to the conversion of the limits. The limit of the convolution converges the convolution of these guys converges uniformly to the convolution of the limits. Right, so these guys are continuous. Each of these guys is continuous. Why does that give us that this is continuous? Take 10 seconds and write something down. Why does it suffice to show?
I was going to say it's just true by uniform convergence, but that's not really asking.
Okay, does somebody want to say why it's true? Or should I have you talk to each other? Do you want to talk to each other? Talk to each. I'm going to leave the room and you can talk to each other. That's actually why I left the room.
I said by uniform convergence it is true. Let's think why. They converge uniformly in the L1 mode, which means we can pick at some point in the sequence they get they're close.
Okay, does anybody want to say? Maybe that was not enough time. But anybody want to tell me why? Why is that enough? Why does these guys being continuous mean that, and they converge uniformly, that this thing is going to be continuous? Jade?
It's a back to the uniform convergence.
Yes.
So it's continuous.
Yes, exactly. So if you've got continuous functions and they converge uniformly, they converge to a uniform. They converge to a continuous function. Right? Yeah. Right. 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 If these guys are continuous, we just showed that this is going to be continuous. Right. These guys individually being continuous means that this thing is continuous. We just showed that. This thing converging uniformly to that thing means that that thing is continuous. Right. So anyway, maybe it's too easy. Okay, so so it suffices to show that these guys can converge uniformly. Okay, so let's do it. So let's prove. Okay, so let's prove that fact. So continuous functions converge uniformly, then the limit is continuous. Okay, so let's prove that, prove the claim. So I want to show that these things, that we can make. We want to show that we have uniform convergence. In other words, that given an epsilon, there exists a big K such that if little k exceeds that big K, then fk convolved with gk, x minus f convolved with g, x is smaller than epsilon for all x, right, uniformly. Okay. Right, that's just the definition of uniform convergence. You need not write it. Okay, so we have fk converging to f, we have gk converging to g, right? Here we want to show that the convolution converges to the convolution here, right? So kind of the obvious move is we're going to slide in we're going to slide in fk convolved with g, right? Right, let me make sure that that's what they did. Yeah, anyway, whichever one it is, it's okay. Okay, we're going to slide in, we're going to say, well, look, let's subtract off an f convolve with gk, say, and add on that same thing, f convolve with gk. Right, so the left-hand side equals this thing. Right? Right, and that's kind of the obvious thing to do because we want to take advantage of the fact that fk converges to f and that gk converges to g. Right. So let's split it up into pieces. Right. So again, by the triangle inequality, we get this is controlled by. Let me write it this way: f convolved with gk minus g of x plus fk minus f convolved with gk x. Right. Okay. So I hope that's you know, that's sort of an obvious move to make. That's the natural move to make, right? Because we have, you know, our hypotheses are that these guys converge to these guys. Right. Right. That's what we know, that the fk converge to f and the g can converge to g. So we want to use that, right? We want to put in somehow fk and the difference between fk and f and the difference between gk and g. Okay, so okay, so what do we do? Let's look at the first term. Consider the first term, f convolved with gk minus g. Right? So that's going to be, by definition, that's 1 over 2 pi, the integral from negative pi to pi, f of y, you know, gk minus g, evaluated at x minus y. X minus y dy. Right? But you see that we're basically done. That's the end, right? Right? Because, you know, again, we use the triangle inequality. Let me write it the other way, since maybe it'll look neater. I'm going to write the convolution the other way. It doesn't matter. I'm going to write it as gk y minus gy dy. I could have written that way from the beginning, I guess. Okay. Now this thing is smaller than b, right? So we get b times the L1 difference between these two things, but that goes to 0.
Yeah.
The end.
Yeah.
The end. Right, and then the other one, same thing, right? So we would have, right? We have these guys are all bounded by some constant b. The difference is that over there we just have f, and here we've got gk. We're convolving against gk, but these guys are all bounded by the same constant b anyway. So that's still the same argument will hold. Okay. we're going way faster than I thought we would. Okay. Okay. Is anybody have questions? Yes? No?
No, go ahead.
Okay. Okay, so, right, so that's it. Well, we've got, oh no, we're not going way faster. Okay, great. Okay. Okay, so okay, so that was the proof of the of continuity, right? That if you convolve two functions, two integrable functions, then you end up with continuous functions. Okay, so now let's go for the number 6. So claim 6, which was that if f and g are integrable, then the Fourier coefficients of the convolution are the product of the Fourier coefficients of the factors. So I'm like jumping one or two chapters ahead. Okay. So okay, and we're going to do this in a very similar way to the. I mean, not exactly. Maybe not at all, but the broad strategy will be the same. Okay, we'll do it first for continuous functions, and then we're going to do it for integral functions, using the continuous case. Okay, so proof case 1. Okay, case 1. Assume that f and g continuous. Okay, then. You just write it out. You say, well, look, I'll write it backwards. Okay. So I'm going to start with the right-hand side rather than left-hand side. So we get the Fourier coefficient of f. So f y e to the negative I and y dy. Okay. And we get the Fourier coefficient of g, which is the same thing. We'll use a different variable, oops, because I want to combine them together into one double integral. So we have these two single integrals, we combine them into one double integral. We get 1 over 2 pi, the integral from negative pi to pi of. So, okay, I'll just write it out. E to the negative I and y. I'm just putting the integral inside the dy. Okay, so I'm just moving this thing inside the other integral. So g of x e to the negative I and x dx dy. So I combine them into one double integral, and then I do a change of variables. So I do a change of variables on this guy. So really not much is going on. 1 over 2 pi. I'm just going to slide it over by y. So g of x minus y e to the minus I and x. I and x minus y, dx dy.
Do we not have to change our bounds because of periodicity?
That's right.
Okay.
We don't have to change the bounds because of periodicity.
Okay.
Yeah, because integrating over one 2 pi period is integrating over any 2 pi period.
Right.
Yeah.
Good.
Okay, now we combine things together and we change the order of integration. So we say, okay, this is going to be 1 over 2 pi negative pi f of y, sorry, 1 over 2 pi negative pi f of y g of x minus y dy. Okay, dy. And then what we have left over is e to the negative I n x dx. Okay. Right, because we have some cancellation occurs, right, and we're just left over the e to the negative I n x, right? But you see what that is, right? That is the convolution. This is the convolution right here, right? This is f convol with g at x. And so what we're getting is the nth Fourier coefficient of the convolution, right? So we get the nth Fourier coefficient. Oops. We get the nth Fourier coefficient of the convolution, right? The nth Fourier coefficient of the convolution. Okay. 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 Everybody, all right? Okay. I hope that was pretty straightforward, right? So if they're continuous, it's just a calculation. We do need to use, the biggest thing we use is Fubini's theorem, which allows us to change the order of integration.
And is that where we are using continuity?
Yes. Okay. Yeah. Okay. Yeah. Let me finish this. Okay. I'm sorry. Yeah. Okay. So okay. So this is case 2. Case 2. Right. So we want to show. So the case 2 is that f and g are integrable. Right. And just as before, we use those sequences. Right. So as before, there exists fk and gk continuous functions such that blah, 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 blah. I'm not going to write it down. Okay. Okay. Well, most importantly, such that fk convolved with gk converges uniformly to f convolved with g. Okay. So and that's actually what we're going to use. So we only have a couple minutes. So I'm just going to I'm going to cheese it a little bit, as was said, as people used to say back when I was a college student. Anyway, I'm going to just sketch it a little bit. So because of the uniform continuity of this, so uniform convergence, so since these guys converge uniformly, then the Fourier coefficients the Fourier coefficients of this converge to the Fourier coefficients of this. Okay. Actually, let me say exactly why that happens. Right. That happens because the Fourier coefficients here, if we're taking the limit as k goes to infinity of the Fourier coefficients right, so we get this y e to the negative x, so e to the negative I n x dx, right? Because of the uniform convergence, you can change the order of integration and limit, right? And so you can slide the limit in, and then you just get the Fourier coefficient of the limit, right? So by uniform convergence, you get the Fourier coefficient. You get the Fourier coefficient of the limit, which is this. Right? You get the. So by uniform convergence. Okay. Okay, so right. So right now we have that the convolution of the Fourier coefficient of convolution converges to this, right? That's what we just showed, right? But we already showed that for continuous functions, this turns into the product, right? For continuous functions, this is the product. Right? Right. So by continuity, so since fk and gk are continuous, we have that this thing turns into that thing. Right? But look, observe. If we look at, observe that fkn actually converges to f hat of, fk hat of n actually converges to f hat of n, right? Once we show that, we'll be done, because then these guys converge to that, but they individually converge to f of n times this one converges to f hat of n, this one converges to g hat of n, and so that will be the end. Right. Once we show this, we're done. Then we're done. Right, we would get that fn hat, gn hat. As k goes to infinity, this turns into that, but it also turns into this, right? And so these guys would be equal to each other, right? Okay, so all we need to show is that this is true. Sorry, it'll just take me one second, right? So you just say, well, look, if you look at the difference, of the coefficients here, well, that's just going to be f minus fk x e to the negative I n x dx. Right? But that's smaller than, by the triangle inequality, that's smaller than this. Right? And this goes to 0 because the fk's converge to f in the L1 norm. This is exactly the L1 difference between f and fk, which we know goes to 0. Right? So this goes to 0, and then the other one also goes to 0. Right? And so the Fourier coefficients of these guys converge to the Fourier coefficient of this guy, and then we're done. Sorry, that was a bit rushed. Maybe I'll do it again at the beginning next time.